Okay then, so now we're going to look at when we use fractional uncertainties. And let's take the case of something I mentioned earlier. Let's say something here which is just a rectangle and 20 centimeters on one side and 40 centimeters on the other side. Now, very easy to work out the area, which would be 20 centimeters times 40 centimeters. And we end up with 800 centimeters squared. Now that's easy. What about the uncertainty in this area though? As I said, we don't have an areaometer, which we can just say, oh, well, half of my smallest increment is this, so that's going to be my absolute uncertainty. No, we have to take the uncertainties of the individual measurements of the 20 and the 40 and combine them in some way to get the uncertainty in the area. So let's call that L1 and L2. So L1 is 20 centimeters, and let's assume that I have a ruler, which the smallest increment is 1 centimeter, an analog ruler. So my absolute uncertainty will be half a centimeter. And let's presume that L2 is a similar thing, similarly measured. So let's use that. Here we go then. How am I going to get the uncertainty of the area? Here's the rule. When multiplying or dividing quantities, which is what we're doing in this case, we're multiplying two lengths in order to obtain the area, we add the fractional uncertainties. Now notice earlier when we subtracted lengths, we subtracted our quantities, we added the absolute uncertainties, the raw uncertainties from our measurements. In this case, multiplying two quantities, we add the fractional uncertainty. So let's go through this step by step. So step one then is obtain the fractional uncertainties. So looking at our values, we had L1, which is 20 centimeters plus minus 0.5 centimeters. So the fractional uncertainty is the uncertainty in L1 divided by L1, 0.5 divided by 20, and there we have 0.025. Let's do the same for L2, which was 40 centimeters plus minus 0.5 centimeters, and we have 0.5 divided by 40, which is 0.0125. There we go. So those are my two fractional uncertainties from my individual length measurements. Now let's follow the rule which I wrote up here. When multiplying or dividing quantities, we add the fractional uncertainties. So we're multiplying L1 and L2 to get the area, so we're going to need to add those fractional uncertainties. And adding those two numbers together gives us, okay, now this is a key number. This is the fractional uncertainty, frac-unc, of the area. Not quite finished though, because we don't want fractional uncertainties as our final numbers. We don't want to say, oh, the area is 800 centimeters squared plus minus a fractional uncertainty. We need to convert this fractional uncertainty of the area back into an absolute number. So step 3, which is convert our new fractional uncertainty back to an absolute uncertainty. Now let's recall the area, which was L1 times L2, was 800 centimeters squared. Now let's remember our definition of fractional uncertainties. the fractional uncertainty of the area is defined as the absolute uncertainty of the area divided by the area. And we've just seen in step 2 that this is equal to 0.0375, that number up the top there. So very simply then, to get the absolute uncertainty, I can rearrange this equation and that gives me an answer of 30 centimeters squared. So that's my final value for the area. So the area was 800 centimeters squared plus or minus 30 centimeters squared. Sorry, I put a cube there. So, just review. When multiplying or dividing quantities, we add the fractional uncertainties. So we multiplied L1 and L2 to obtain the area. So step 1, obtain the fractional uncertainties, which I did there. Step 2, add those to get the fractional uncertainty of the area, and then convert the fractional uncertainty back to the absolute uncertainty.